All right, guys, so here's part 2. So in this part, we will cover angular kinematics, the conversion between angular and linear variables, rotational kinetic energy, moment of inertia, torque, Newton's second law for rotation, and work and power from torque. So starting off with the non-long answer problems, the first problem says that we have a point mass, which is 2.5 kilograms, which is moving in a circle of radius 10 centimeters. So let's go ahead and draw that. We have an object that's moving in a circle. It has a radius of 0.1 meters, 10 centimeters. And there's a force of 12 newtons on the object that's tangent to the circle. So tangent to the circle means it comes off like this. It has a force of 12 newtons. And we want to know, well, we want to know a whole bunch of stuff. The first thing that we want to know is the torque on the object. So the torque is the distance from the axis of rotation times the force times the sine of the angle between them. So here, our distance from the axis of rotation is just our radius, our 0.1 meters. And the angle between these things is 90 degrees. So our torque is our 0.1 meters times our 12 newtons times sine of 90, which is 1. So our torque is 1.2 Newton meters. Next, we want to know what its moment of inertia is. Now, the moment of inertia of a point mass is always its mass times its distance from the axis of rotation squared. So here we have our 2.5 kilograms times our distance from axis of rotation is the radius of our circle. So it's 0.1 meters squared. And so this is 0.025 kilogram meter squared. Now we want to know what its angular acceleration is. Well, we know that the sum of the torques on an object is equal to its moment of inertia times its angular acceleration. We only have one torque in this case, it's this one. And so our 1.2 Newton meters has to be equal to our moment of inertia times our angular acceleration. So if we divide by our moment of inertia, then our angular acceleration is 48 radians per second squared. Next, we want to know the tangential acceleration. So the angular acceleration is related to the tangential acceleration by the distance from the axis of rotation. So all I have to do is multiply by our 0.1. And their tangential acceleration is 4.8 meters per second squared. And if it starts from rest, what is the angular velocity after 12 revolutions? So this is an angular kinematics problem. We know our angular acceleration. So we know that it starts from rest. So we can use this equation. Our angular velocity squared is equal to our initial angular velocity squared plus 2 times the angular acceleration times the angular displacement. Now, we don't really know the angular displacement. We know that it's 12 revolutions, but we need to convert that to radians. So 12 revolutions. In each revolution, there are 2 pi radians, which means that our angular displacement here is 24 pi radians. And we start from rest. So our angular velocity squared is twice our angular acceleration, which we said was 48 radians per second squared, times our angular displacement, which is 24 pi. So if we take the square root, then we can see that our angular velocity is plus or minus 85.1 radians per second. Our angular acceleration is positive, which means that since we started from rest, our angular velocity should be as well. So it's positive 85.1 radians per second. Now, next we want to know what distance has the mass traveled at this time. So distance, linear distance, is related to our angular variables like this. Physical distance that our object has traveled is equal to our distance from our axis of rotation times our angular displacement when it's in radians. We already found that this thing was 24 pi, and our distance from our axis of rotation we know is 0.1 meters. So this is 7.53 meters. You also want to know what is the tangential velocity at this time. So the tangential velocity is our distance from our axis of rotation times our angular velocity. We found that our angular velocity was, whatever it was, found that it was 85.1. So we multiply that by our distance from our axis of rotation. So this is 8.51 meters per second. Next, we want to know the centripetal acceleration. Well, the centripetal acceleration is our tangential velocity squared over r. But since our tangential velocity is r omega, this is equivalent to our distance from our axis of rotation times the angular velocity squared. So this is our 0.1 meter times our 85.1 squared. So this is 724 meters per second squared. Next, you want to know how much work has been done on the mass at this time. Well, the work done from a torque is the torque integrated over the angle. Now our torque here is constant, so we can pull it out. And so our total work is just our torque multiplied by our angular displacement. So the total work done then is our 1.2 meter torque, Newton meter, times our angular displacement, which we said was 24 pi. So that's 90.5 joules. This is the total amount of work that has been done up to this time where it rotated through these 24 pi radians. And the last thing it wants, or no, there's several more things. It wants the instantaneous power. Well, the instantaneous power due to a torque is the torque times the angular velocity at that time. So here our torque is our 1.2 Newton meters. Our angular velocity here is 85.1 radians per second. So this is 102 watts. Watts, remember, is the unit for power. And also, what is the rotational kinetic energy? Well, the kinetic energy for a rotating object is 1/2 times its moment of inertia times its angular velocity squared. So for us, this is our 1/2. We found that our moment of inertia was 0.025. And our angular velocity was our 85.1. So our kinetic energy then here is are 90.5 joules. Now, it shouldn't be surprising that these things are equal to each other because all of the work done is being converted to kinetic energy. And in fact, we could have instantly just written this down from looking at this here. Either way, that's fine. Okay, that was number one. Number two says a sphere of mass 1 kilogram and radius 2 centimeters is rotating about an axis 10 centimeters away from its edge. So let's draw that. We have a sphere. It has a mass of 1 kilogram. It has a radius of 0.02 meters. It's the same as 2 centimeters. And it's rotating about an axis 10 centimeters away. It's rotating about this thing. So this is our 0.1 meter. And we want to know the moment of inertia here. Well, if you look at your table of moment of inertias, this one won't be on there. But what will be on there is the moment of inertia of a sphere rotating about an axis through its center. And the moment of inertia in this case is 2/5 the mass of the sphere times the radius of the sphere squared. And we can use parallel axis theorem to find this new moment of inertia. So the parallel axis theorem says that our new moment of inertia is the moment of inertia about the center of mass plus the mass of our object times the distance away from the center of mass squared. Okay, so our new moment of inertia is our initial one, because this goes through the center of mass of our sphere, plus the mass of our sphere times the distance to the axis. Now the distance is not 0.1, because this is the distance from the center of mass. So it's actually 0.1 plus 0.02, which is 0.12 squared. Now our R is our 0.02, our mass is 1 kilogram. So we can just plug this into our calculator. And we find that our moment of inertia for the sphere is 0.015 kilogram meters squared. All right, easy enough. Okay, our next problem says Jennifer is trying to loosen a bolt with a 0.3 meter wrench when the wrench becomes stuck at an angle of 30 degrees with respect to the vertical. She puts her entire 600 Newton weight onto the wrench, but the bolt doesn't budge. What is the magnitude of the frictional torque on the bolt? All right. So we have a wrench that's on a bolt. And set an angle of 30 degrees with respect to the vertical. And Jennifer puts her entire, the wrench is 0.3 meters. She puts her entire force, her entire weight onto the end of the wrench. So this is 600 newtons, okay? But it doesn't budge. So since it doesn't budge, that means its angular acceleration is 0, which means that the sum of the torques on our object is 0 too. So we have two torques here. We have the torque that Jennifer applies. So whatever, the torque from Jennifer. And we also have the torque from the friction in the bolt, what keeps the bolt from actually moving. So first, let's figure out the signs here. So she's applying a torque down, which means, so our axis of rotation points like this. Our force is down like this. That means it's going to try to make it go clockwise. So her torque is negative, which means that our frictional torque must be positive. These things have to be equal to 0. So the magnitude of our frictional force, of our frictional torque rather, is equal to the magnitude of Jennifer's torque. Okay, so if we find Jennifer's torque, then we also have the magnitude of the frictional torque. All All right, so we only have to find Jennifer's torque. So Jennifer's torque is our distance from our axis of rotation. Our axis of rotation is in the center of our bolt here. So it's just the length of a wrench times the force that she's applying times sine of the angle between them. So we know the force that she's applying is her weight, or 600 newtons. So the only thing we have to figure out is the angle. And so what angle do we want? We want the angle between the axis of rotation, our distance from our axis of rotation and the force. So if we extend this vector here, we want this angle, okay? And what do we know? Here, let me redraw this a bit bigger. This is going straight down. We want this angle, and we know that this angle is 30 degrees. So if we extended this up, this angle is 30 degrees. And these two angles together make 180, which means that our theta here must be 150 degrees. So our frictional torque, which has the same magnitude as Jennifer's torque, is our distance from our axis of rotation, which is our 0.3 meters, times our force, which is our 600 newtons, times the sine of our angle, which is 150 degrees. So our frictional torque has a magnitude of 90 Newton meters. Okay. All right, so on to the next one. Our next problem says, relative to some coordinate system, an object is located at 11 meters in the x direction, minus 7.1 meters in the y direction, plus 4 meters in the z direction. And we apply a force, 21 newtons in the x direction, 36 newtons in the y direction, and minus 4 newtons in the z direction. We want to know the torque on the object. So as a vector, torque is our distance from our axis of rotation cross into our force. So we just have to find the cross product between these two vectors. And so if we do that, we can draw, oops, that was bad. We can take the determinant of a matrix whose first row are the unit vectors. Second row is our first vector, and whose third row is our last vector. So we need to take the determinant of this matrix. If we wanted to, we could write the matrix on either side, which makes this a little bit easier, but I won't do that here. So to find the x component, we look at the diagonal this way. And because we went to the right, it's positive. So we have negative 7.1 meters times negative 4 newtons, and that's positive. And then we go in the opposite direction. Since we're going left, it's negative. So we subtract from that our 4 meters times our 36 newtons, and that's all in the x direction because the x is where we started. Okay, can do the same thing with J. First, we go to the left. And so we have, it's positive, or sorry, first we go to the right, and it's positive because we're going to the right. We have our 4 meters times our 21 newtons. And then we can go to the left, which is negative. So we have minus our 11 meters times our negative 4 newtons. And that's all in the y direction. Then we add the z part. So first we go to the right, which makes it positive. So it's positive 11 meters times our 36 newtons. Then we go to the left, which is negative. So we have our negative minus 7.1 meters times our 21 newtons. And that's all in the z direction. So if you simplify this, we get negative 115.6 Newton meters in the x direction. Plus 128 Newton meters in the y direction. Plus 545.1 Newton meters in the z direction. Okay. So we just have to take the cross product and that's it. All right. Our next problem says an object has one non-zero force on it. Is it possible for the net force to be 0 newtons? No. If you have one force on an object, this is 5. If you have one force on an object, there's nothing to counterbalance that force. The net force cannot be 0 on it. Now, is it possible for the net torque to be 0? Yes. There's different ways, but one way is to apply the force at the axis of rotation. So for instance, if you have a door that has hinges here and here, if you push against the hinges here, it doesn't matter how hard you push, you will never get the door to open. Alternatively, you could push at a 180-degree angle. So if you pushed from the side on the door, it doesn't matter how hard you push, you're never going to get the door to open. So with one force, you can't have a 0 net force, but you can have a 0 net torque. Okay. The next problem says the Earth is a sphere of mass 5.97 times 10 to the 24 kilograms. And it has a radius of 6,380 kilometers or 6.38 million meters. And it rotates on an axis through its center of mass once per day. What is its rotational kinetic energy? Well, the rotational kinetic energy, we know, is an object's moment of inertia times its angular velocity squared times 1/2. So first, we need to know the moment of inertia of the Earth. Well, if you look up in a table, the moment of inertia of a sphere is 2/5 its mass times its radius squared. So in the case for Earth, our mass is this thing, our radius is this, which means that our moment of inertia is (9.72 times 10 to the 37 kilogram meter squared). This is a huge number, but that's okay because the Earth is extremely massive and it's got a pretty big radius. Okay, but that's not what we're after. We're after the rotational kinetic energy. So we need to find the angular velocity of the Earth. Well, the Earth rotates once per day. So that's 2 pi radians over 1 day. In 1 day, there's 24 hours. In 1 hour, there's 60 minutes. In 1 minute, there's 60 seconds. So overall, that is an angular velocity of 7.27 times 10 to the minus 5th radians per second. All right, so now we have everything we need to find the kinetic energy. It's 1/2 times our moment of inertia, which is this thing, times our angular velocity squared. So what we end up getting is that our kinetic energy is 2.57 times 10 to the 29 joules. So that's the kinetic energy in the Earth due to its rotation. All right. Now, our last question, our last non-long answer question is, your little brother is interested in physics. Explain to him how the right-hand rule works. Well, we have several right-hand rules, but the important one is if you want to take a cross product between two vectors A and B. Let's say we have A, we have B. You put the fingers of your hand along the A vector, and then you curl them along the B vector. So one way for me to do that is to rotate my hand like this, and then my thumb points in the direction of the cross product. Okay, so for our long answer problem, our first one says, find the moment of inertia of a thin uniform washer that has mass M, outer radius R1, inner radius R2, and surface mass density sigma. So I didn't say this, but through the center of mass. All right, so this is problem one. So a washer has concentric circles. We said our outer radius was R1, and our inner radius was R2. And we want to find the moment of inertia about an axis through the center of mass. Okay, well, we know the moment of inertia of a point mass is its mass times its distance from the axis of rotation squared. So if we break this thing up into a whole bunch of different little point masses, our moment of inertia is the integral over r squared over all these little point masses. Now, the whole thing has a mass m, and it has a surface mass density of sigma. So that's a surface mass density, which means that sigma times the area is equal to the mass. So if we differentiate both sides of this, this is uniform, so it doesn't get differentiated. So sigma times a little infinitesimal area unit is equal to dm. So I can replace that here. So our moment of inertia is our distance from our axis of rotation squared times sigma times dA. Okay, that's all well and good. Sigma is a constant, it can come out. So I'm left with sigma r squared dA. Now, what is the area of a little piece here? Well, sorry, my dog decided it was time to play. But the area, a little infinitesimal piece of our surface here that makes an angle d phi, and this distance is dr, then our infinitesimal area is dr times r d phi, right? So the fact that it's not a square and it's actually a little piece of a cone, this distance is r, this distance is r plus dr. We want this area. The fact that it's a piece of a cone instead of a square doesn't really matter because we're working with infinitesimals. So we can just use this distance times this distance. So this distance is dr, this distance is r d phi. So our total area is r dr d phi. So we can replace that here. So our moment of inertia is our surface mass times r cubed dr d phi. So we can integrate over these things independently. And we make an entire circle here. So for the d phi integral, we just go from 0 to 2 pi, or minus pi to pi, it doesn't matter. And then for our r integral, we go from r2 to r1, right? We don't go from 0 because there's no mass in the middle of our washer here. So we only go from r2 to r1. Okay, so if we integrate over the phi part, we just pick up a 2 pi. So we have 2 pi sigma times this integral. Well, we have r cubed. To integrate it, we increase the number by 1 and then divide by it. So we have r to the 4th over 4. And then we evaluate this from r2 to r1. And so our moment of inertia is 2 pi sigma r1 to the 4th over 4 minus r2 to the 4th over 4. So if we pull out the 4, then our moment of inertia is pi over 2 sigma times r1 to the 4th minus r2 to the 4th. Now we don't want our moment of inertia in terms of sigma. We want it in terms of our total mass. So our total mass is our area times sigma. The area of our entire washer here is the area of this outer circle minus the area of this inner circle that we're missing. So this is our number sigma times pi r1 squared minus pi r2 squared. Okay. And so now we want to replace this with our moment of inertia. But we have our things to the 4th power instead of to the 2nd power like we have here. But anytime we have a squared minus b squared, we can write this as a plus b times a minus b. So our moment of inertia then is r1 squared plus r2 squared times r1 squared minus r2 squared. So now we're looking a lot closer. So if we have pi times sigma times this thing, that is the area. So without the sigma, that's the area. And then with the sigma, that's just our mass. So we can replace that with our mass. And our moment of inertia is our mass over 2 times r1 squared plus r2 squared. Okay. So that one's a little harder than I intended it to be. So I won't give you one that bad on the test, but I could give you one that was like a rod that's rotating about some point that's not on it, or rotating about the end, or rotating about some place in the middle somewhere, and then make you integrate to find it. Okay. So our next problem is Janice and Janet, a 20 kilogram kid and a 25 kilogram kid, are playing on a merry-go-round, which is a cylinder of mass 100 kilograms and radius 1 meter. Both children are sitting on the far edge of the merry-go-round, and their mom pushes tangential to the cylinder with a constant force of 25 newtons. Okay, so we have our cylinder has a radius of 1 meter. It has a mass of 100 kilograms. And mom is pushing tangent to the cylinder with 25 newtons. Okay, and we want to know, first off, the kids are sitting on the edge. It doesn't matter where they're sitting, just that they're on the edge. The first thing we want to know is what is the moment of inertia of the merry-go-round with the children on it? Well, a merry-go-round rotates an axis through its center like this. And so the moment of inertia of a cylinder rotating about a line through its center like that is 1/2 mr squared. But we don't just have the cylinder, we also have the children that are sitting on the ends. So it says to treat the children as point masses, and a point mass has a moment of inertia of its mass times its distance to the axis of rotation squared. So in this case, all of our r's here are the same, and they're the same as the radius of our cylinder. So our total moment of inertia is the moment of inertia of the cylinder. Let's call that radius capital R, plus the moment of inertia of each child. So this is the mass of the cylinder. So plus, let's say Janice's mass, and she's sitting at the radius of the cylinder because she's on the far outside. And then we also have Janet, and she's also sitting at the same place. So this is our total moment of inertia. So here we use 100 kilograms for the mass of the cylinder itself and 1 meter, since that's the radius. Here we use Janet's mass, or Janice's mass, which was whichever, 20 or 25 kilograms. Here we use the other mass. And so if we put that together, and our moment of inertia is 95 kilogram meters squared. The next thing asks us, what is the torque that the mother is applying? So torque, the force that she's applying is tangential to the circle. So our torque is our distance from our axis of rotation times our force times the sine of the angle between those things. Here, our R vector and our force are perpendicular. So sine of 90 is 1. And the distance that she's doing it at is the radius of the cylinder. So the torque that she's applying is our 1 meter times our 25 newtons, which is 25 Newton meters. Then it says, if the merry-go-round was initially at rest, what is the angular velocity after 15 seconds? So to find the angular velocity, first we need to find the angular acceleration. So we can use Newton's second law for rotation, which says that the sum of the torques on an object are equal to its moment of inertia times its angular acceleration. There's only one torque here, and it's this one. So I have 25 Newton meters is equal to our moment of inertia, which is our 95 kilogram meters squared, times our angular acceleration. So our angular acceleration is 25 over 95. It's 0.26 radians per second squared. Now we want to find the angular velocity after 15 seconds. So we know that the angular velocity is our initial angular velocity plus our angular acceleration times time. We started from rest, so this is 0. So we just have our 0.26 radians per second squared times our 15 seconds. So our angular velocity here is 3.95 radians per second. And next we want to know, what is the total work she has done during this time? Well, we know that the total work done by a torque is the torque integrated over the angle. Our torque here is just a number, so it pops out of the integral. So it's our torque times our angular displacement. So we need to find what this angular displacement is. And we can use kinematics again to find that. So one of our kinematic equations is that our angle is our initial angle plus our initial angular velocity times time plus 1/2 our angular acceleration times time squared. Now we're interested only in the change in the angle. So we can just rewrite this like this. Okay, and we started from rest. So our angular displacement is our 1/2 our angular acceleration, which we found was 0.26 radians per second squared, times our time squared, which is 15 seconds. So our angular displacement then is 29.3 radians. Our work is our torque times this change in angle. So we found that our torque was 25 Newton meters. You multiply that by our 29.3 radians. We find that the total work done so far is 731 joules. We're also asked for the instantaneous power. The power at any time is the torque times the angular velocity. The torque was our 25 Newton meters, and our angular velocity we found to be 3.95 radians per second. So we just multiply these things together. And we get that the power at this time is 98.8 watts. All right, so I'll see you guys for the next video.